Okay, so folks, welcome to lesson one. Just a reminder that anytime we're starting something new, we have to spend a lot of time getting the basics down. So a lot of this will end up being a lot of me talking and a lot of terminology. I also know that a bunch of you have taken physics and you know a lot of these basics. So this first unit in particular, at least till the end of this first unit, a lot of this stuff's going to be familiar. So just go with the flow. Just in case people haven't covered it, or it's been a while and they haven't used it in a while, I do want to go through everything very carefully. And then once we get to the end of this unit and beyond, well, we're going to see there's going to be a lot of new stuff coming along. Okay, so I want to start by introducing our old friend back. So Broccoli Bear is back. And he's going to help us set us up for this whole idea of vectors. And remember that Broccoli Bear could only live in a one-dimensional world, meaning he could only walk or move in a line. Okay, and the way we described this motion, or where he was, and we use sort of, I'll stick with position, distance, and velocity. Velocity, speed, and of course it could be extended to acceleration. But if we wanted to talk about how far he was from the reference point, well, that's just given by some positive number. Okay, and it didn't matter whether he was 3 meters from the reference point on this side or 3 meters from the reference point on that side. The distance away, again, some positive number, was just described how far he was from the reference point. But then if we wanted more information and we wanted to know, well, not just how far is he from the reference point, but on which side of the reference point, all right? So this idea of position, okay? So this position is not the same as that position, despite the fact that the distance is the same, okay? And can somebody just quickly tell me what we use to distinguish this position versus that position? What did we have when it came to working with real numbers that just allowed us to distinguish, there you go, positive and negative values? All right, so if he's 3 meters and he's on this side, so we say his position is positive 3, and if he's there 3 meters away, his position is negative 3. Okay, and similarly for something like speed and velocity. If I'm just saying, Broccoli Bear is moving at 2 meters per second, okay, that he's moving 2 meters per second in that direction doesn't matter. The speed is the same, okay? How is the distance traveled with respect to time? But if we want to talk about this idea of velocity, which includes not just how fast he's going, but in one direction. And again, we could use a sign that if I'm moving towards the positive direction, moving at 2 meters per second, and in a negative direction, negative 2 meters per second. So in other words, anything that has to do with Broccoli Bear's, position and motion can all be described using the real number system. Okay, so you can sort of think of this as a number line, and this is 0, and everything can be described using real numbers, with positive and negative representing this idea of direction. Okay. Well, of course, Broccoli Bear at some point, especially right around now, it's getting to be warm, and Broccoli Bear is going to want to get out of his lair and start living in a two-dimensional. Bear can move in 2 dimensions, so he can move in any location he wants. So we need some other way of representing not just moving at 2 meters per second, but moving at 2 meters per second in that direction, as opposed to moving at 2 meters per second in this direction. Okay, and as I think a lot of you know, this is where we use this idea of a vector. Okay, so if you're just talking about, say Broccoli Bear's speed, again, that's still, like before, just some positive number. So 2 meters per second, that's how fast he's moving, all right? As opposed to moving at 2 meters per second in this direction. So I think, as you saw when I first opened this up, okay, Well, one way of describing that is to use this, directed line segment or a ray or an arrow to represent not just moving at a particular speed, but in what direction. So the direction of the arrow tells us where broccoli bear's moving, okay? And then the length of the arrow represents that numerical quantity that tells us how fast he's moving, okay? So this is the idea of needing this idea of vectors to describe these quantities where direction is important, okay? But now we see that we've got these sort of two competing types of measures. This idea of just a numerical quantity, and this idea of a quantity that contains both the numerical quantity and the direction. Okay, and so this is where we need to distinguish these two things, and so. And so this is where we have the idea of a scalar and a vector. So I've got a little shtick here that I forgot to prepare. So let me just get my shtick going. And so we don't want to just talk about this idea of a numerical quantity, which we're going to refer to as a scalar, okay, and a vector quantity, which we're going to call a vector. So this contains just a numerical quantity like the speed, 2 meters per second, as opposed to this one here, which tells you not just 2 meters per second, but 2 meters per second in a particular direction. Okay, so this is where we're going to have the ultimate scalar versus vector smackdown. There we go. So, a battle for the ages for sure. Okay, so who's going to give us some ideas as to what constitutes a scalar and what's a vector? So we already gave a few examples. So maybe those of you who've taken physics, think about, just give me some stuff that would be a vector as opposed to a scalar.
So a scalar is just a magnitude value. So
yeah, so give me some examples. Give me some examples.
Speed, distance.
Good. Let's get somebody else to give us something else. So what else? So speed and distance. Good. What else? Number of kids, time, energy. Okay, great. And then we see vector, the idea of a velocity. What else would be a vector? Where else is something like, acceleration? Okay, because you want to know in what direction. Good. Jerk. Perfect. Force. Okay, because if I'm if I have this object here, let's just see why is visualizer not working. Okay, this should work in a second, hopefully. Give me just a second. There you go. If I have this object, it makes a difference whether I apply a force in that direction or whether I apply the force in this direction. It causes a different motion. Okay, so let's just take a look at a couple of examples here. So you may have noticed that I have posted, so I'm going to try to do this, is post not just the worksheets, but the solutions beforehand in case people want to take a look at that. So again, here, time, speed, here, mass, which just represents how much stuff, something is made up of. That's a scalar quantity. It doesn't have any kind of directional component, whereas a vector quantity will. It has what we call a magnitude. Okay, so that's what we refer to as the numerical value, okay, or scalar value, and of course the direction, okay? And we see here different ways of describing this direction. So here we might be using cardinal directions like going west. Okay, we might be using up and down. So say force, if you think about something like weight, okay, the force due to gravity, 90 newtons downwards, okay? Or like in, one dimension, you can think of that as being a vector 10 centimeters to the left of the origin. So anything that's described using both a numerical or scalar quantity, which is your magnitude, and a direction, which can be given in many ways. Okay, and so here in terms of, if we take a look at this next question, which is, how do we represent these quantities? Well, we already talked about this idea of using a ray or an arrow. Okay, so going from, say, A to B, you could use points to represent this. Okay, and what happens is that the length of this arrow represents the magnitude. Now, say this is 3 centimeters long, doesn't mean the magnitude that the vector is representing is necessarily 3. It could be 6 if each centimeter represents 2 units of your measure. Okay. Now, another way that I think, certainly if you've taken physics, you'd have seen is using these cardinal directions. Okay, is to specify the magnitude, so give that explicitly, and then the direction is given with respect to this cardinal plane. Okay, so what does this mean? It means you start east and then you go 30 degrees towards the north. All right, and these, this is really good for drawing a picture. This is going to be very useful when we start doing calculations. All right, so this will be a very useful one, but as I say here, there's going to be other ways. Well, in particular, one certain way to describe vectors that's going to be particularly important for us. And can you see where this is going to break down? This whole idea of using the cardinal directions, because, Broccoli Bear, gets out of his lair so he can suddenly start moving, all along the ground. But what if, bears at some point evolve? What might they want to do at some point?
Climb trees.
They might want to climb trees. Actually, they probably still can. They could already do that. There you go. Is they might want to, learn how to fly. They might be building rocket ships, and at some point, that's it. You're going to need to talk about 3 dimensions. Okay. I'm not sure if we're going to get to the 4th dimension, although I will reference that towards the very end of this course. So we definitely will be talking 4 dimensions and beyond at the very end of this course. So I'd be happy about that, Keegan. All right. And if you think about it, you realize that this setup for describing a vector with some numerical values starts to fall apart. All right. So we're going to have to come up with a whole different way of describing vectors that adapts itself well to 3 dimensions. Okay, and just a couple of things on notation here. So we save just, regular old letters to represent scalar quantities or numerical quantities like we've done before. If you're using x, that represents some real number, okay, or possibly an integer, depending on what you're working with. Whereas if you want to represent a vector, we use this little arrow above your letter. Okay, not surprisingly, since the arrow is kind of our nice pictorial representation of a vector. All right, so this represents both a magnitude and the direction. But if you just want to talk about the magnitude of the vector, we're going to use these 2 bars. Now, you have to be very careful because these 2 bars do not represent absolute value. Okay, they represent magnitude. Now, we're going to talk a little later on how it's not by surprise that we use the same symbol. And you probably think about why we would co-opt the same symbol. Technically not. So Charlie's asking whether it's the same thing. Technically not. Okay. So we'll see that, maybe one is a special case of the other, but they're not in and of themselves the same thing. Okay. So it'll be very clear when this represents absolute value and when it represents magnitude of a vector. If you got a vector inside, it's magnitude. If you got a number inside, it's absolute value. All right. So any questions before I move on? So let's go back to our, now that we've figured out our smackdown here. All right. And let's talk about how we describe vectors comparing to each other. Okay, now you notice here that another possible option would have been to describe the angle between the two vectors as perhaps placing them, if this is tail and this is tip. Okay. So somebody's asking about the square brackets. Yeah, you can use that notation. It's, there's different schools of thought on that one there. But yes, if you want to, so anything I'm going to say, anything that has to do with something that you're already doing in physics, you can keep doing it that way. Okay. So either way is acceptable to me. So let's take a look here. Is we've got this, tail to tip, and then placing the next vector, tail to tip. So we call this setup tip to tail because the tip of the first joins up with the tail of the second. Okay, and it would not be unreasonable to think of that angle as being the angle between the two vectors. Okay, but it also could be defined by placing them what we call tail to tail. Okay, so I suppose either one could work, but we need to come up with a standard. And the standard is that when we're talking about the angle between two vectors, we're talking about the angle when they're placed tail to tail. All right. So let's keep that in mind because that's going to become very important when we're solving problems later on. Now, one thing I'd like to ask you is, look what I did is I just started moving this vector along, like I had every right to do so. Well, I guess I should maybe justify why I have a right to just move this thing around. Does anybody want to give me a reasoning as to why it's okay to take this arrow, which represents some vector, and then just move it to some other location? Okay. So I'm going to stick. So I have a couple of answers here, okay, and they all have good stuff in them. But essentially, a lot of these references is that what constitutes a vector? What constitutes a vector is a magnitude, which we said is represented by the length of this arrow and the direction where the arrow is pointing. So that I take the arrow in this position or that position, it still has the same length and it's still pointing in the same direction. So the great thing, and that is like one of the beautiful thing about vectors, about how they define vectors, is that they're movable. You can move them around anywhere, that this vector in this position represents the exact same vector as if it was in that position. Okay, that's what ends up making them so useful, as we're going to see later on. Okay, so they was definitely very smart in defining vectors in this way. Okay, so here, this is how we define the angle between two vectors, because we're going to see that sometimes this is how the information is given to us. They might not describe this vector as 20 kilometers east, 10 degrees north. They'll describe a vector with respect to another vector. So it's important to understand what the angle between them represents. All right. So here we start to now think about what it means for these vectors to have certain characteristics. And we already talked about this idea of what it means for two vectors to be equal. Okay. So equal just means that their length is the same or their magnitude is the same and they're pointing in the same direction. Okay. Now this idea of opposite. Okay. We also define this idea of being opposites. So in other words, having the exact same magnitude, but in the exact opposite direction. Okay. So this is how we define opposite vectors. Now, can you think about a way that I might use notation to compare these two vectors? So say this blue vector was vector u. Do I have something that would be a reasonable
Negative u?
There you go, negative u. And one of the things that you're going to see, and what we're going to get to at the very end of this sheet, is that we're going to make a lot of connections, okay, to vectors, whether it's in 2 dimensions or 3 dimensions, and we're actually going to make sure that everything we define in 2 and 3 dimensions kind of works out in 1 dimension also. Okay, so what did we use to represent the difference between, if this is position u, well, we used negative u to represent being in the exact opposite direction, okay, same distance away. So think of 4. What's the opposite of 4? Negative 4. Okay, so we're going to see later on, I'm going to show you the sheet, that the way we designate opposite vectors notation-wise is by using negative. We're co-opting this idea of negative, okay? And what does it mean for vectors to be parallel? Well, it might be tempting to say that as long as they're in the same direction, even if they're not the same length, they're parallel. But in fact, we go a little further than that. They can also be in the opposite direction. So all of these vectors are considered to be parallel vectors. Okay. So here, one of the questions is, are 2 vectors that are equal parallel? They certainly are. Okay. So 2 vectors that are equal are parallel. 2 vectors that are parallel are not necessarily equal. Okay. All right. So what we're doing here is, like I said, we're starting to get some of the language. Okay, in fact, let's sort of take a look at that on the sheet here, because I don't know if everybody necessarily has that right in front of them. Okay, so again here, in order to be equal, same magnitude, same direction. So we see that the magnitudes are the same, even though, and the vectors are the same. Whereas when they're opposite, same magnitude, opposite direction. So while they are not the same vector, their magnitudes are equal. Okay, so the next question I ask is how we could represent other relationships with respect to sorry, I keep losing the chat here. Give me just a second. There we go. How we represent vectors that are related to this, okay? And we're going to see that this is going to bring us to a very important starting point, all right? So if we go back to, go back for a second here, okay? And I'm just going to, for a second, because I just want to change something here. Just give me a second. I'm going to stop projecting for one quick second. Okay, we're back. Just give me a second. So I asked this idea of how you could represent a vector with a magnitude 3 times larger as some given vector. So say this is my vector v, and I want a vector that's exactly 3 times longer, but in the same direction. So in other words, the only thing I'm changing, so there you go, about 2.2, and this is about 6.6, so 3 times longer. So how would I represent a vector that's exactly 3 times longer? So we don't have to change the direction. The only thing we have to do is, okay. So I have a couple of answers here, okay, and I see that 3v is exactly the answer, okay. That if this is vector v, okay, this vector here is going to be the vector 3v. Sort of makes sense that since the only thing we're changing with this vector is the magnitude, that we're just going to need a scalar quantity to make that change. But of course, there's nothing to say that that scalar quantity that we multiply might not itself be negative. And of course, what is the effect of a negative? We saw that it represented a vector in the opposite direction. Okay, so when we're trying to represent a vector that's 3 times longer, okay, the way we represent that is by just multiplying the given vector by 3. Okay, and what does this represent? It represents a vector that's in the exact same direction as my original vector v, okay, but multiplying it by this scalar, okay, just makes it 3 times longer. Okay, when we multiply by a scalar that's negative, okay, in this case here, negative 1/2, well, the positive portion still has the effect of changing the magnitude, so half as long, and the effect of the negative is to give it the opposite direction, okay? And so since we're taking a vector and we're multiplying it by a scalar quantity, it's not too surprising that what we call this operation is scalar multiplication. All right? So let's take a look at this idea of scalar multiplication. Okay, so if I have some vector v, okay, and I look at the vector k times v, all right, well, what's it going to do? It's going to give me a vector that's in the same direction, and this is going to be k times longer. Now, can somebody tell me what little thing I have to be careful of here with the way I've written everything? What's the issue that comes about?
K has to be positive.
There you go. This assumes that k is positive, okay? But remember what we saw in this example here. This positive portion still represents the effect on the magnitude of the vector. So what would I have to add here to incorporate the fact that, if I want to represent the change in the magnitude, what could I add to this, to what I wrote?
Value of k.
There you go, is what we say. As we say, it's absolute value of k times longer than the original vector. Now, somebody said greater than 1, but in the end, it could be, half times greater just means it's half the length. So definitely k could be between 0 and 1, okay? So when we're talking about some new vector kv, okay, if we're looking for the absolute value of this new vector kv, okay, while it's tempting to say that it's k times the magnitude of the original vector v, we have to add absolute value symbols here, okay, in the case that k is negative, okay? But this is where we have to be careful that it's all about context. This represents magnitude, and this represents absolute value. Okay? So what we've just defined now is this operation called scalar multiplication. Okay? And the word that's very important here is this word operation. Okay? Because this now opens up a whole door. Because if we start treating these vectors in a similar way to the way we treat, say, things like numbers or things like functions now, like we learned last year, is do they constitute a set of objects, mathematical objects that we can operate on? Okay, can we add them together? Can we subtract two vectors? We're seeing here that it makes sense to multiply a vector by a scalar. Can we multiply two vectors together? Can we square two vectors? Like what do any of these things mean? And we're going to see that some of these things have a meaning and some of them, well, might not translate so well to this idea of vectors, okay? And so that's one of the things we're going to be working on over the next little bit, is trying to determine what types of operations we can perform on vectors. In fact, it's going to be a long-term project, okay, as we go along. But the first one that we see, the first operation that we're defining on this group of objects called vectors is this idea of scalar multiplication. Now, this is something I'll talk about again later on, but everything makes sense, I think, this idea of multiplying by a scalar, except perhaps for one particular number. Is there one value of k that might present us a bit of, is what if k is equal to 0? Right? So what does it mean to have 0 times the vector v? Okay. Well, if I use this definition for how the magnitude, well, it tells us that 0v must have a magnitude of 0. Okay. But what does it mean for a vector to have a magnitude of 0? So if this is my starting point, where's my ending point to this vector? Tell me quick.
In the same place.
There you go. There's actually no vector. Okay. So that means, how do we even define direction? So this is where we need to define this perhaps in a slightly different way than we define any other vector. Okay. So what we define is this thing called the 0 vector. Okay. So the 0 vector is not the same as the number 0. It's considered a vector that has magnitude of 0. And what we say is no specified direction, because if I have this starting point, it's not like I'm saying I'm going 0 meters in that direction or that direction or that direction. Okay. So it's a bit of a special vector that represents something which has no direction, okay, and has magnitude of 0. Now, what we're going to have to determine is why it's important to define this vector. Because if it wasn't necessary for me to define it, I just wouldn't even bother. You know, I could describe, scalar multiplication as just being multiplied by any non-zero constant. But we're going to see as soon as tomorrow why it's actually important to define this 0 vector. Okay. And maybe you can even think about why 0 is an important number with respect to real numbers. All right. So I'm going to want you to think a little bit about the next question. The next question says, how can you create a vector? Okay, a little exercise, but it's going to be a little exercise that's going to turn out to be quite useful for us later on. It says, how can you create a vector with the same direction as v? Okay, so you're trying to create a new vector that has the same direction as some given vector, but has a magnitude of 1. Okay, so take a second. So don't put the answer out right away. Give everybody a minute to try to think about how you might create a vector that has the same magnitude, the same direction as some given vector v, but has magnitude exactly 1. Okay, we're getting some feedback on somebody's okay, it might be Andrea there. I think we're getting some feedback on your
No, mine is muted. I have a little dongle that mutes it.
Okay. So, who's got a suggestion for me? Okay. So it looks like the suggestion we have is that we use the magnitude of that vector to help us create this unit vector. So let's take a look at an example here. Okay, if I have my vector here, that's 20 kilometers per hour, so it's a velocity vector going in the northward direction. So the only thing I want to change is the magnitude. And do we now have an operation that allows us to, so I notice here someone said to the power of 0. We haven't actually defined exponents yet. okay? We'll have to see if there's a meaning for that. So when you think about the only thing we've actually defined is this idea of scalar multiplication. So the question is can you use scalar multiplication to take this magnitude of 20 and turn it into magnitude of 1, okay? And the idea here is, well, what about just multiplying that given vector by 1 over its magnitude, okay? Because remember how we defined the magnitude of a scalar multiple of a vector, okay? It's the absolute value of the scalar multiple times the magnitude of the vector itself. So if I take this vector with magnitude 20 and I multiply it by 1 over 20, well, we notice that 1 over 20 is positive, so it won't give us the opposite, meaning it's going to give us a vector in the same direction, okay? And then the effect of the 1 over 20 is to multiply the magnitude by that number, which of course is just 1, okay? So here in general, what we say is that if we want to create a vector of magnitude 1, we just multiply by 1 over its magnitude, or we do allow ourselves, okay, to use the word division, because remember that division is just multiplying by the reciprocal, okay? We can say by dividing by its magnitude, okay? Now, anytime something takes on a particular importance in mathematics, well, one of the things we usually do is we give it its own symbol. So because unit vectors are going to turn out to be quite useful for us, we actually give them their own symbol, okay? And this is the idea of v hat. So v hat, or I think sometimes people call it caret. That's what that, I guess that symbol is called. This just represents still a vector, but very particularly what we call a unit vector, a vector of magnitude 1. So given any vector, if I want a vector that's in the exact same direction but has magnitude exactly 1, I just have to divide it by its own magnitude, okay? So for now, it's just a novelty, but we're going to see later on how creating these unit vectors in the same direction as a given vector is going to turn out to be a useful thing for us, okay? So there's one last thing I'd like to talk about today, but before I get to that, are there any questions that we want to ask in general? Okay, I'm going to assume a lot of this stuff is, is at least somewhat familiar to most people, but are there any questions we want to ask? No? Okay. So there is an urban legend, okay, that out there's some mysterious math teacher teaching, teaching grade 6, 7, and 8 students, and does not work with the real number system, okay? Teaches everything in terms of vectors, okay? So there is no multiplication of numbers. You don't do 2 times 3. You multiply the vector 2 and the vector 3, okay? So how can that be? Well, how might we define a vector? Well, it would be, so let's go back to our, I've got it here somewhere here. Okay. So let's use this same idea of a vector. So here's a vector. All right. Okay. And the idea is I can even think of it, if I want to think of relating numbers to vectors, where would I place this vector if I wanted to represent a number? Where would I place this vector if I wanted to represent a traditional number? There you go, starting at 0. So this vector here, okay, would be the vector 5. Now, of course, what I mean by the vector 5, and I hate having to do this, but I'm gonna, I'm gonna give it a try. This would be the vector 5. Of course, with a little arrow, okay? Which is equivalent to the number 5, okay? And this here, well, I guess would be the vector 3, okay? So, can we still do scalar multiplication? Well, can I multiply this vector 5 by 2? Yeah. Okay, so it has the same effect. So basically it's going to take that vector 5, double its length, and it's going to give me the vector 10. Similar to the way I would get the number 10 if I just multiplied 2 by 5. Okay, that's great. And if I wanted to create an opposite vector, well, the same thing would happen, as I just, take my number 5 and turn it into my number -5. Okay, and this vector here would just be the vector -5. All right, but what if I want to go further? What if I take the vector 5 and the vector 3 and I want to add them together? Let's say I want to explore this idea of adding two vectors together. Well, since I want it to give me the same result as adding two numbers, presumably, what do I want this to be equal to if I add them together? And be very careful. So no, be very careful. I'm having people say 8. Ah, the vector 8. I want it to be equal to the vector 8. Okay, so in other words, I want it to be equal to this vector here. I want it to be equal to the vector 8. So the question is, so if I was just adding numbers, I'd say, oh, just 3 plus 5 is equal to the number 8. But now I have to work with these vectors. Now, how could I combine these vectors in order for them to give me the vector 8? There you go. This idea of putting them tip to tail. That if I take vector 3, and remember, vector 3 is movable. So, vector 3 starts here. Notice I'm drawing them one on top of the other just so that, it's clear. But technically, this would be vector 5, and this would be vector 3. And nothing stops me from taking vector 3 and moving it to wherever I want. And so when I put vector 3 tip to tail with vector 5, I get vector 8. And so what this gives us is an idea as to how I might define vector addition in general. Okay? Because remember what I said earlier is we want to try to define everything in 2 dimensions, 3 dimensions, so that when we collapse it down to 1 dimension, it essentially works out to the way, good old-fashioned operations on numbers occur. Now, at some point, we might have to lose that at some point, but at least for the basic operations, we'd like that to be the case, okay? And so similarly, if I want to take, the number 5, and I want to subtract the number 2, or subtract the vector 2, oh, that didn't work. Let's try again. Take the vector 5 and I want to subtract the vector 2. Can somebody give me an idea as to how I might do that?
You have -2.
Okay, I could take a -2, in other words, take the opposite, and then add it. And remember how we add? We add by putting it tip to tail. So if I take this vector 5 and I add the opposite of vector 3, look what it gives me. Sorry, the opposite of vector 2, what does it give me? It just gives me the vector 3, which is exactly what I would want to happen. That 5 plus -3 gives me, 5 plus, I keep saying -3, 5 plus -2 gives me the vector 3. Okay, so in other words, it looks as though we can perform additions and subtractions very similar to the way we perform additions and subtractions here. So we can still do scalar multiplication. I can take this vector 2 multiplied by the scalar 3, okay, gives me the vector 6, something that's in the same direction but 3 times longer, or multiplied by a negative number, so I get something that's 2 times longer. absolute value of 2, but in the opposite direction. And similarly here, we can do that with addition, okay? And the way in which we add is by adding the vectors tip to tail, okay? So it gives us the result we want it to give us. So vector 2 plus vector 3, or vector 3 plus vector 2 gives us the vector 5, okay? And then, similar to what we do with numbers, is subtraction is just the sum of the negative, or the sum of the opposite. So if I want to define this idea of vector 6 minus vector 4, I can just think of it as the vector 6 plus the opposite of the vector 4, so that I'm recycling addition to help me define this idea of subtraction. Okay? So let's just take a look at what we've done so far. Okay? So as I set up the notes, if anybody has any questions they'd like to ask. Okay, so let's just do a quick recap here. So you'll notice that I just posted all the notes all at once because I think it's just going to make it easier since people are going to be doing this at different times. So what do we need to know? We describe this idea of what a scalar is, quantity that's just represented by a number. A vector needs also a direction. Okay, we have some notation here. So here sometimes you have the arrow that just has an arrow at the top. Sometimes in textbooks you'll just see a bolded value. That's more for older textbook because it was harder typeset to get those arrows. And we can talk about the vector from point A to point B. So how do we? Here's the starting point. Here's the ending point. And just put an arrow above them to represent the fact that it's a vector. Okay, you can use this idea of an arrow. You can use this idea of cardinal directions, and we're going to see some other ones. Okay, you need to understand the notation of the magnitude, and you need to, very important, make sure you understand that anytime we say the angle between two vectors, we're talking about the vectors placed tail to tail. Okay, equal, opposite, and parallel. And then lastly, our first official operation on vectors, this idea of scalar multiplication. Okay, so if you multiply by a scalar, okay, here I have it as k not equal to 0, but we've seen how it does make sense to have a 0 vector. We'll talk a bit more about that last time. Okay, but understanding that when you're finding the magnitude, which is a positive number, make sure that if k is negative, that you're taking its absolute value. Okay. And lastly, this idea of a unit vector is a vector that specifically has a magnitude of 1, and there's a v hat notation. And if you want to take any vector and create a unit vector in the same direction, you just take the vector and divide by its magnitude. All right, so this is just our introduction. Next class, we're going to go a little more into the other operations that we're going to start with, and then we're going to do some applications to force and velocity. So that's sort of where things are going to look a lot like physics. But then after that, we're going to take a whole new approach to vectors that I think should be new for all, if not some, if not all the people. So any questions on this lesson before we end it off? Okay, so I'm going to post the homework in about 10-15 minutes, and we're going to reconvene tomorrow at 9:30 for those who are following these lessons. Okay, so I'm going to stop the recording. Again, last call for questions before we go.